So hi everyone. So in this class let me discuss a very important result, that is Cauchy's general principle of convergence. So this result have came several times in your question paper. So everywhere every semester this question is there in your question paper. So you try to see it very carefully. Okay, this is a 5-mark question. So they ask state and prove general principle of convergence, or state and prove Cauchy's general principle of convergence. So this is there in your question paper several times. You see it very carefully. This is a very easy result. Okay, so your statement of the result is a sequence is convergent if and only if it is a Cauchy sequence. So here if and only if condition is there. So we have to take using convergent sequence, we have to prove it is a Cauchy sequence, and using Cauchy sequence we have to prove it is a convergent sequence. Okay, because of if and only if condition is there. So first part we take a convergent sequence. Using the definition of convergent sequence, we modified the definition in the form of Cauchy sequence. Okay, so using convergent sequence we show it is a Cauchy sequence using and the converse part, that is because of if and only if condition is there. Using Cauchy sequence definition we prove it is a convergent sequence. So proof follows like this. So first we take A and B a convergent sequence, and that is converging to L, and we have to show that it is a Cauchy sequence. So using the definition of your convergent sequence, I am writing that let epsilon greater than 0 be given, then there exists a positive integer m such that an minus L is less than epsilon by 2 for all n greater than equal to m. So in your previous definition I have taken that modulus of an minus L is less than epsilon, because your epsilon is very small quantity, so I am making it very small. Okay, so if I divide epsilon by 2, then it doesn't matter. Okay, because it is a negligible quantity. So because of I have to make a n minus am is less than epsilon, so because of that reason I am taking this epsilon as epsilon by 2. So here I am replacing, for in particular for n is equal to m, we have this term becomes am minus L is less than epsilon by 2. So therefore it will become, while now I am taking an minus am is equal to, so I add and subtract L. Okay, so that is minus L plus L, minus into minus plus. Okay, so your an minus L is, so using your modulus property I can write it as this is less than or equal to an minus L plus am minus L. So you know that an minus L is less than epsilon by 2 and am minus L is less than epsilon by 2. So epsilon by 2, half epsilon. So then it will become 1, that is epsilon. So thus an minus am is less than epsilon for all n greater than equal to m. So that implies that sequence n is a Cauchy sequence. So what I did here, so first I have taken the definition of your convergent sequence. Using your convergent definition, I have written your definition in the form of like this. Okay, so here I have replaced the value n by m, then you get this. Okay, so after that I have taken, that is modulus of an minus am is equal to this. So after that I have add and subtracted your L. So after using modulus property I have rewritten this term in the form of like this. So after I have substituted the value of an minus L and am minus L, so then it will become this. So this satisfies the definition of your Cauchy sequence. Okay, so now the converse part. So here I take n is a Cauchy sequence, and you know that every Cauchy sequence is bounded. Previously, in previous class we have seen that every Cauchy sequence is bounded. Therefore an is bounded. Since every bounded sequence has a limit point. Okay, so therefore n has a limit point, that is say L. Okay, an has a limit point, that is L. So now we have to show that an converges to L. Means if you have to show that an converges to L, that is a sequence converges to L. Okay, so here I am taking, let epsilon greater than 0 be given. Epsilon greater than 0 be given. Since an is a Cauchy sequence, there exists a positive integer m such that an minus am is less than epsilon by 3. So here in the place of epsilon I am taking epsilon by 3, because later we have to make it means epsilon. Because of that reason I am taking this as epsilon by 3. So don't worry about that. Okay, this quantity for all n greater than equal to m. So let epsilon greater than 0 be given. Since using the definition of Cauchy sequence, we can write it as modulus of n minus am is less than epsilon by 3 for all n greater than equal to m. So I take it as equation number 3. Okay, so later using the definition of limit point of a sequence, I can say your modulus of n minus am is less than epsilon by 3. Okay, so means here limit point L. Okay, since L is a limit point of sequence L, and every neighborhood of L contains infinitely many terms of n. Yes, so using the definition of limit point of a sequence L, we can say L is the limit point of an. So every neighborhood of L contains infinitely many terms of an. Therefore I can say n belongs to, means your so there in the case of n minus am is less than epsilon by 3, so there n belongs to L minus epsilon by 3 comma L plus epsilon by 3. So therefore I can write here, means upper bound and as well as lower bound, means it lies between, sequence n lies between lower bound as well as upper bound. So therefore I can directly write this as an belongs to L minus epsilon by 3 comma L plus epsilon by 3 for infinitely many values of n. So in particular we can find a positive integer k greater than m such that ak belongs to L minus epsilon by 3 plus comma L plus epsilon by 3. So here your k is also greater than m, so therefore your ak also belongs to L minus epsilon by 3 comma L plus epsilon by 3. So using the definition of your limit point of a sequence, we can say that is ak minus L is also less than epsilon by 3. Since k is greater than m, therefore from equation 3 we have ak minus am is less than epsilon by 3. So k is greater than m, so therefore we can write modulus of ak minus am is less than epsilon by 3. So here I take modulus of an minus L is less than so here I am taking modulus of an minus L. So here I add and subtract am, I add and subtract ak. So then it will become an minus am plus am minus ak plus ak minus L. So using modulus property we can write modulus of an minus less than or equal to, this term is less than or equal to an minus am plus am minus ak plus ak minus L. So replace the value of this, the an minus am is less than, using equation 3 we can write this is epsilon by 3, ak minus am is less than equation 5, this is epsilon by 3, ak minus L also less than epsilon by using 4. So using by 3, 4, 5. So by 3, 4 and 5 we can write this is less than epsilon by 3, this is less than epsilon by 3, this is less than epsilon by 3. Thus your an minus L is less than epsilon by 3. This is okay, less than epsilon by 3 for all n greater than equal to m. So this is the definition of your convergent sequence. Therefore the sequence an converges to L. So this is the proof of your above theorem, that is Cauchy's general principle for convergence. So this theorem came several times even in our question paper, and this is a very important result for the point of examinations. So you read it very carefully. This is a simple result. Okay, so we are solving this result using your definition of convergent sequence, okay, and Cauchy sequence and limit point of a sequence. So these three The definitions are very important to prove this result. So if you have any doubts regarding this, you can ask question to me or send your questions to my WhatsApp number and clarify your doubts. Thank you one and all.